Hello everyone, welcome to another video in our AP Calculus course. This is our first video and first lesson from Unit 3. In this lesson, we're going to be looking at some basic rules for finding the derivative. Currently, all we have available to us is the definition of the derivative. But as you apply the definition, hopefully you notice that some of the answers were really similar and seem kind of repetitive. And if we were able to use the limit definition of the derivative on a specific equation type or family of equations, we could find a rule to help us find the derivative quickly. And so that's what this unit is going to be all about. We're going to try and learn all the rules so we don't have to rely on the rather tedious and slow process that you've used thus far. Okay, so I do want to handle a little bit of notation business right here. I like to slowly introduce the notation of calculus to you. It can be a little bit overwhelming at first, so I want to just slowly introduce it, and then as I do, I'll explain it little by little. So here's just a little bit more. The rate of change in one variable must be determined with respect to the rate of change in another variable. It doesn't make any sense for us to describe how fast one thing is changing without describing it as a function of something else's change. For example, I don't care how much your y is changing. If your x isn't changing at all, the y probably isn't going to change either. So we have to describe the amount of change in y based on a change in x. And when we get into multivariable calculus, which is not this course, you'll notice that we'll leave different variables constant and let other variables change. So we'll look at the effect of different parts of it. So because we have to take a look at the derivative, the rate of change of one variable with respect to another, we're going to say that f prime of x, the derivative with respect to x, can be written as either what we've already seen, which is f prime of x, or we're going to say it can be written as dy dx. This d in higher math courses is often written as a lowercase Greek delta, but we'll just use the letter d. And so it's the differential in y over the differential in x. In other words, it's an infinitesimally small change in y per infinitesimally small change in x. That's what the derivative really is. It's describing how much does the y change when you infinitely small change the x. And so yes, because we're changing the x such a small amount, the y is also infinitely a small change, but not the same. Now, dy over dx can be abbreviated as y prime, and I want you to start realizing that. And in fact, y prime oftentimes can mean other things than dy over dx, which is a little confusing, but for us, we're going to say y prime is the same as dy dx, and that's usually how you read it. You don't write it dy, you don't read it dy over dx, you just say dy dx, and everybody knows what you mean. The operation of taking a derivative with respect to x is written d over dx. So for example, if I was to take the derivative with respect to x, which is how you read that, of y, then the answer is dy over dx. And you'll notice that's pretty much the same rules for fractions. You can think of this as a numerator and the y as a numerator. It's not the same thing. This is not fraction multiplication, but it works out that way in notation because they want it to look like regular algebra. And so a lot of times the rules are written in a way that make algebraic sense. And so even though they are kind of different, because we're talking about infinitesimals, they end up looking the same, which is really convenient. Okay, so with that in mind, let's introduce, using this notation, the derivative with respect to x of x to some power n. And we're going to define that n is simply a real number. And that means that no matter what the exponent is, if it's a real number, the derivative with respect to x of x to the n is n times x to the n minus 1. So we simply take the exponent and we multiply by it, and we subtract 1 by it. So let's practice using that, okay? So that's our formula. So let's find the derivative with respect to x of f of x equals x to the fourth. So with f of x, I'll write it as f prime of x. All right, I'll bring down the 4, making it 4x cubed, and that's it. You bring down the exponent and multiply by it and subtract 1 for the power. All right, let's go to the next one. Okay, this is not written in the right form for us. In calculus class, we don't usually like radicals. We like fractional exponents so that we can use our what's called the power rule. So I'm going to write that as x to the 1/2. And now I have a choice. I can write y prime or dy dx. Since it's new, let's use our new notation. dy dx for the derivative. Bring down the exponent and subtract 1. Well, 1/2 minus 1 is a negative 1/2. And there we have it. Now, we could rewrite this as a radical. We could also move this to the denominator, making it 1 over 2 times the square root of x. But we're just going to leave it like that. That's fine. We're not going to do any simplifying right now. All right, letter C. Well, this is also not written in what I would call the proper calculus form. Let's realize that if we have a variable in the denominator, that's the same thing as it being in the numerator with a negative exponent. And since this is just a 1, I'll leave it. I won't write the 1 times x to negative 4. Then g prime of x, the derivative of g with respect to x, is negative 4x to the negative 5th power. Be careful when you do this. Some students want to say negative 3 because they subtract 4 minus 1, but negative 4 minus 1 is a negative 5. Okay? All right, here we are at letter D, f of x equals 7. Well, what I'd like you to consider is that this is f of x equals 7 times x to the 0 power. And anything to the 0 power is 1. So then if I take f prime of this, I'll bring down the 0, and 0 times 7 is 0. And I'm kind of jumping ahead there. We haven't really talked about all those different properties I've said, but I wanted to give an idea why while the derivative of a constant is 0, because we're bringing down that exponent 0 and multiplying by it. But let's do this more rigorously. Let's prove this rule. We haven't proved the rule for the power rule yet, and at the end of this lesson, I will go over a proof, but only for positive integers at this time. So let's use the limit definition of the derivative to show that this is in fact 0. It has a neat little subtlety. So the limit as h goes to 0 of f of x, which is c, plus h. Well, there is no x, right? You know what? I tell you what. Let's write down the formula: f of x plus h minus f of x all over h. That's the formula for the derivative. And in this problem, our f of x is merely the constant c. So I need to replace, when I do this, the first step is to do f of x plus h. So I need to replace all the x's here with x plus h, but there is no x, so it's still just a c. Then minus f of x, which is just a c all over h. Well, this becomes the limit as h goes to 0 of 0 over h. Now, if you plug in h, 0 for h right now, you'll get 0 over 0, which is confusing because we know that that's indeterminate. But what I'm going to tell you is this is not at all an indeterminate form, and let me explain why. When we say 0 over 0 is indeterminate, what we mean is a number going to 0 divided by a number going to 0 is indeterminate. This is not a number going to 0. This is 0. And so h is some infinitely small number, but not exactly 0. And if you divide 0 by any number that's not exactly 0, the result is 0. So there's a difference between number going to 0 over 0 and the true 0 over a number going to 0. True 0 divided by anything not 0 is 0. And remember, when I say h goes to 0, h never actually gets to exactly 0. So the derivative of a constant we have proved with the limit definition is 0. We haven't proven this. We could certainly do the limit definition for x squared, x cubed, x to the fourth, and I recommend you do it and confirm that this pattern exists, that it's the exponent times x to the old exponent minus 1. But we haven't proved it yet. It has to come from the limit definition, but I'm not going to show that till the end of the lesson. All right, let's take a look at our constant multiple rule. If we have the derivative with respect to x of c times f of x, where c is some constant, that is equal to c times the derivative with respect to x of f of x. And I'm going to let you prove that. It is a perfect application of the property that you can pull a constant out of a limit. It's really a two-step proof, so I'm going to leave that to you to prove it. But do understand, it all goes back to the limit definition of the derivative. This is not me changing the rules here or making the game easier or harder. It's just the facts. Combining the power rule with the constant rule, we get this kind of idea, that if you have a number times x to the n, when you bring down the exponent, we just multiply the current coefficient times that new exponent. And so we'll use that in just a second. Okay, the sum and difference rule. The derivative with respect to x of f of x plus g of x is equal to f prime of x plus g prime of x. That's a nice little easy proof. I'm going to leave that to you as an exercise in the homework. Okay, so what does all this mean? Well, what it means is that constants just come along for the ride. Okay, you'll probably hear me say that 100 times. Calculus teachers love to say that. It comes along for the ride. They just come along and multiply by whatever the answer is. What else does it mean? It means we don't have to look at a problem like 1.2 and do this monstrosity of a derivative definition with it. This would take forever to do with the limit definition. Instead, we can do it part by part by part. We just have to take the derivative of this part, this part, this part, and that part. We'll do them one at a time, and then that'll be the result. That's what the sum and difference is telling us, that we can take the derivative of each part. I do want you to notice that there is no, and I say sum and difference because add, subtract, really kind of two sides of the same coin. But there is no multiply or divide rule yet. You know, it doesn't, you can't, it's more complicated, so I'm not giving it to you, okay? All right, so let's take a look at this. The derivative with respect to x of f of x. So here's what we're going to do. We're going to take this exponent. Oh, you know what? This problem is not ready for me to take the derivative of. I need to rewrite it first. This is 4x cubed minus 5x to the negative 2 plus 7x minus 3. Now I'm ready to take the derivative. So f prime of x is equal to, bring down the 3. 3 times 4 is 12. And the 3 becomes a 2. Bring down the negative 2. Negative 5 times a negative 2 is a plus 10x. Be careful here. Negative 3. All right. 7x to the first. 1 times 7 is 7. And x to the 0 is just 1. So it's just a 7. So when you take the derivative of x to the first power, you just get the constant. And the derivative constant is 0, so it's gone. It's just gone. And that's it. That's our derivative. All right. Let's do the next one. Okay, so remember I said that there is no division rule for us yet because it's a little more complicated, so we're not doing it today. So the only way we can do this is to actually divide first. So we're going to divide each one of these terms by x. That becomes 4x squared. X squared over x is just x, so minus 3x, and then plus 7. And I'm just going to say x to the negative 1, or you could call it over 7 over x, but I like it with a negative exponent. And we haven't used y prime in a while, so let's use y prime. Bring down the exponent. 2 times 4 is 8. X to the first. And then that just becomes 3 times 1 is 3. And then x is 0 is just a 1. Alright, then bring down the exponent. I get a negative 7x. And subtract 1 gives me negative 2. Alright, it's time for you to do some practice problems. Please pause the video. Be sure you rewrite the function first to get it in the right form. That means no square roots and no variables in the denominator. We like negative exponents when we're doing this. So do that, take the derivative, and then we'll check our answers. Alright, let's see how you did. You could have called this y prime, or our new symbol, dy dx. So I'll use dy dx. 4 times 2 is 8. So this is 8x to the first minus 3. Alright, Next I have f of x equals 1 over x. We don't like that. We're going to rewrite that as f of x equals x to the negative 1. Then f prime of x is equal to negative x to the negative 2. Alright, next one. We need to rewrite this. This is, oops, wrong variable. T squared minus 4 over t to the 1/2, alright? But that's still not quite right. Let's rewrite one more time. And you can certainly do this in one step. I just wanted to show both. I'm going to move this t to the 1/2 up to the numerator, making it a negative 1/2. Alright, now it's just where I get to use the power rule. Bring down the 2, makes it 2t to the first. Bring down negative 1/2. Negative 4 times negative 1/2 is a plus 2. T, and subtract 1 is a negative 3 over 2. Alright? Okay. Okay, so you have another practice problem. It says use the graph to estimate the slope of a tangent line, then verify your prediction with the derivative. But it would probably help if you knew the equation. So let's write down the equation since I didn't include that. This is y equals x to the 2/3 minus 2. That's the equation of this curve, and you'll need it when you find the derivative. So estimate on the tangent line, then use the derivative to verify your result. So pause the video, give it a try. Alright, so the tangent line at 1, 1 is, I'm thinking, something like up 2 over 4 or up 2 over 1, 3, something like that. Certainly there is a 2/3 here, so that would make sense. Alright, so how do we get the slope of a tangent line? The slope of the tangent line is the rise over run at that one spot right there. Slope of the tangent line is the change in y over the change in x. That's what rise over run is, dy dx. It is the derivative. So let's find the dy over dx equation. Bring down the exponent, you get 2/3 x to the negative 1/3, and then that 2 goes away. So then dy dx evaluated at x equals 1. So they gave us the x and the y value, but I'm not using the y because my derivative only has an x in it. The slope of the tangent line for a function is dependent entirely on the x coordinate. And so I usually write it, I say dy dx such that with that vertical bar or with the value of, and I put x equals 1 down here as a subscript. If you're using y prime, you can say something like that. So that's kind of a nice thing about using y prime. I'll say 2/3 times 1 to the negative 1/3. Now, 1 to any power whatsoever is simply 1. So that's pretty easy. So 1 times 2/3 is 2/3, and that is what we were thinking, up 2 over 3. So the slope of the tangent line is indeed 2/3. Alright, what do we got next? Okay, got another practice problem. I want you to write the equation of the tangent line to this equation at the point 17. Pause the video and give it a try. Okay, let's see how you did. So, how do you get the slope of the tangent line? We get the slope from the derivative. So that should be pretty easy now. We know how to do that. Bring down the exponent, you get 6x to the first plus 5. Now, that's the equation for the slope of the tangent line at any value x. So I'll evaluate it at the x value of 1, since that's what it's telling me here. So I get 6 times 1 plus 5 is 11. So I know the slope of the tangent line at 1 is 11. Now I'll write the equation of the tangent line. And we usually prefer point slope form because it shows both the point of tangency and the slope of the tangent line. So point slope form is a really preferred style of writing the equation of the line. Of course, you need to be able to convert this to other forms as needed, but that's a lesson for another day. So for us, we're just going to leave it in point slope form. Alright, next, let's talk about some more rules. The derivative of sine and cosine. Again, I'm going to prove this to you at the end of the lesson. I don't want to crowd our lesson up with a bunch of proofs right now. Instead, I'll wait and do it at the end for those of you that are particularly interested. But if you do the limit definition of the derivative on the sine of x, you will find that the derivative with respect to x of sine of x is, believe it or not, cosine of x. And that the derivative with respect to x of cosine of x is negative sine of x. So they are related to each other in their derivatives. Really an interesting feature. So now let's apply that. So find the derivative of y equals 7 over x squared plus 5 cosine of x right now. So dy over dx is, well, we need to fix this first. 7x to the negative 2 plus 5 cosine of x. This becomes a negative 14 x to the negative third minus 5 sine x. And I think that pretty much takes care of everything. All that's left is some proofs. So that's what I'm going to do. So if you're not at all interested in the proofs of these different properties, I'll let you turn off the video now. But I hope you'll stay with me as we go through some of them. Let's start with the power rule. We're going to prove this rule, that the derivative with respect to x of x to the n is equal to n times x to the n minus 1. Now, in order to prove this for all real numbers, I actually need quite a bit of things we haven't learned yet. So it's just kind of interesting. We'll get to revisit this proof time and time again and make it more and more general. But for now, I'm only going to prove it for n as an element of the positive integers. I could say we've already proved it for n equals 0 because we've shown that when n equals 0 it's a constant, and we did show that the derivative of a constant is 0. So I'm going to prove it now for the positive integers. We're going to use it for all numbers, for exponents, but for now I'm just going to prove it for a positive integer exponent. Alright, so we need to understand these are not shortcuts. These are just simply remembering the results of doing the limit process. This is the only process we have. Well, okay, one of two, because we also have the alternate definition. But in this case, it works best, I think, this way, but you can prove it both ways. So we know that it's f of x plus h minus f of x all over h. So we need to expand x plus h to the n. And so if you were to expand, say, x plus h squared, you would get x squared plus 2xh plus h squared. If you were to expand x plus h cubed, you get x cubed plus 3x squared h plus 3xh squared plus h. And hopefully in your pre-calculus class you learned that these are actually values from Pascal's triangle. Even x plus h to the first is just, 1x plus 1h, and even x plus h to the 0 would be just a 1. So these coefficients here are from Pascal's triangle. But what's important to realize is actually just these two columns here. So whenever I expand this out, every term is the first term in my expansion will not have an h, no matter what, and will always have a coefficient of 1. The second term will have an h to the first power and will have an exponent that is equal to the power of what we're expanding it. So when we had a power of 2, we had a 2 here. When we do a power of 3, we have a 3 here. We have a power of 4, we have a 4 here. And that's going to continue forever. So what that means is that if I were to expand this out, that this is going to be x to the n plus x to the n minus 1 will be the next power here, h to the first, and the power here will be an n. Do we agree? No matter what n is, it'll be that number will be the second one. And then there's going to be a bunch of other stuff that's all going to have an h squared, h cubed, h to the fourth. They're all going to be h values higher than 1 up until they get to h to the n. Okay, so the last term won't have an x in it, it'll have an h to the n. All the others are going to have like an h squared, an h cubed, h to the fourth, as depending on how high n is. Okay, then minus x to the n still from that, all over h. Okay, so let's look at what we have here. Well, you can see that the x to the n's go away, and we remember from doing the limit definition that if you have any term in the numerator that doesn't have an h, you messed up. And we agree that there's only going to be one term in this expansion that doesn't have an h in it, and it's going to be that x to the n that'll cancel out. All the others will have an h in it. So I'm going to divide through by the h. So this will be an nx to the n minus 1, but there'll be no h. Then that next term, if we were to write it out, I mean, it depends which one it is. It's, it'll be something, it'll be some number. It turns out that it's actually like you use combinatorics, in choose, and in this case, in choose 2, x to the n minus 2, h to the second, and then etc. But you don't need to worry about that. All you need to realize is that there's still going to be an h there. Oh, not h to the second, sorry. H to the first, because we divided by h. So no matter what power of n, that the power of n is going to affect how many terms there are, but they are all going to have an h. So I'm not going to confuse us with this kind of combinatoric stuff. Okay, instead I'm just going to say plus stuff times an h, okay? And we're taking and I forgot to write limit. How bad I get on to all my students about that, and then I forgot to do it myself. So the limit as h goes to 0. So when I take a limit, all of this stuff is going to have an h in it, is going to be times 0. It's going to be gone. And this is simply nx to the n minus 1, which is what we were trying to show. So I hope you agree that the derivative with respect to x of x to the n, for n being a positive integer, must be n times x to the n minus 1. Alright, next, let's talk about the derivative of sine of x. The derivative with respect to x of sine of x, what does that equal? Well, that is equal to the limit, and I'll use the original definition of h goes to 0, of sine of x plus h minus sine of x all over h. And it turns out this is actually a pretty easy application of your angle sum formulas you learned in pre-calc. So this is the limit as h goes to 0 of sine x cosine h plus cosine x sine h minus sine of x. Keep in mind, I like the parentheses around the argument of sine and cosine, but you need to be comfortable with the idea that you don't need them. The argument continues until you either write another cosine or a plus. If you need plus inside your argument, you do have to have parentheses. So I needed these parentheses here, I didn't here. Okay, so let's see what we can do with that. Well, if I rewrite this, I can actually group this and this together, and so that's exactly what I'm going to do. So sine of x cosine of h minus the sine of x plus the cosine of x sine of h all over h. Now I'm going to factor out, scroll down just a little bit, I'm going to factor out sine of x. So I get the sine of x times cosine of h minus 1. Alright, plus, then I have cosine x sine h all over h. Alright, now I'm going to do some limit properties, and I'm going to split this up quite a bit actually. I'm going to call this the limit as h goes to 0 of sine of x times the limit as h goes to 0 of cosine of h minus 1 over h plus, I'm dividing each term by h. So when I divide this term by h, I can't divide both sine of x and cosine h minus 1. I have to pick one of them. I pick the cosine of h minus 1. Over here, same thing. I have to pick one of these to divide by h. So I'm going to say plus the limit as h goes to 0. I'm not going to divide that one. I'll just say cosine of x times, I will divide this one now. Okay, so this is just a constant, believe it or not, because we're dealing with h going to 0, and there's no h in sine of x, so this is just sine of x. And we learned earlier that 1 minus cosine theta over theta as theta goes to 0 is 0. Also, cosine of theta minus 1 over theta as theta goes to 0 is 0. So that's 0. We've learned that property. It's actually proved using the squeeze theorem. Okay, plus, now this here, this is again just a constant, so this is just the cosine of x. And then the limit as h goes to 0, well, we learned that as the limit as theta goes to 0 of sine of theta over theta is 1, so that's just a 1. So that's 0 plus cosine of x times 1, well, that is cosine of x. It's just a formula for the derivative of sine of x. I'm going to leave you to prove the derivative of cosine of x is negative sine of x. It's a neat little exercise. And that's it for today.